Now let's take a look at what happens if we just let this crab keep on eating. What is this population going to end up looking like? Again, this is something where you might want to stop the video and write down your prediction of what is going to occur. Okay, if every snail looks exactly like its parent, which is the way the simulation is set up now, any snail with this bright yellow shell will have an offspring with a bright yellow shell, and so on. There's a limit to what's going to happen in this population, and let's see where that limit is. We better reproduce some snails because we're running out. Crab's going through munching. You notice that things aren't changing very much anymore. They were changing pretty rapidly at first when we first put the crab in, but now not so much. And now that there's only one color of shell left in this entire population, the simulation isn't going to change anymore at all. The reason is that we've run out of variation. There is no snail in this population that has an advantage over any other snail. All the shells are the same thickness, and as long as there isn't mutation, the population is no longer going to be able to evolve thicker shells. Let's see if we allow a little bit of mutation to happen. What's going to occur in this population if we allow a little bit of mutation to happen? So now if I click this checkbox, what that means is that the offspring of these snails can be slightly different from their parents. And keep in mind, that doesn't mean that the shells are necessarily going to be thicker. They might be thinner. It's totally random whether or not an offspring is going to have a mutation that makes its shell thicker or whether it's going to have a mutation that makes its shell thinner. Okay, but let's see what this does to the evolution of this population. Okay, look, we've got some thicker ones and some thinner shells. Again, and now we're getting some really thick shells showing up. And remember that the mutations aren't trying to go in the direction of thicker shells. It's just that every once in a while, a new mutant arises that has a thicker shell, and that mutant does better than any snail in this population ever did before. Pretty soon here, we're getting up into these really thick shells that the crabs can barely open at all. Notice that that crab just passed over some of those really thick-shelled snails without trying to eat them. And that's what they do in the wild. Oh, that one's a struggle to eat. Wow, took a while. They did it. I think you can see where this is going. If there is a crab exerting selection pressure on a population, only the snails with the very thick shells are going to be left. But the shells can't get any thicker than the thickest ones that were already in the population unless mutation is present as well. What mutation does, and all that mutation does in evolution, is that it provides new variations for the filter to act on. And sometimes it can be very rare, but sometimes those mutations are going to be a better solution to some life challenge, like a green crab, than any snail has ever seen before. So by itself, natural selection can obviously change a population a considerable amount. It's only, though, when you add on these random mutations to that filter that you get a system of evolutionary changes that can completely overhaul a population and turn up something that you've never seen before. As impressive as they can be, though, I want to point something out. Mutation and natural selection are not all powerful. In particular, I'd like you to notice something. They never look ahead. They can't. The organisms you see today are the ones that survived all the filters of the past, and they ought to be very good at dealing with the challenges that their ancestors faced over and over and over again. But this does not necessarily mean that they'll be able to cope with a totally new challenge, one that their ancestors have never seen. This is important in environmental science because human beings tend to throw challenges at organisms that are totally new. We change the world in ways that organisms have never seen before. In particular, one of the things we do is move other species around, and this can be a real problem. Here, for example, is a group of snails that have lived with crabs for a long time. And let's see what happens. Here they are. They're go ahead and breeding. There's mutations happening all the time. This population is evolving. Let's see what happens if you throw a bunch of crabs in there. There's 1, 2, 3. Heck, let's throw a lot of them in there. Here we go. That's a lot of crabs. There's 6, 7, 8. That's probably enough. Okay, let's see what happens here. I mean, it's carnage. It's almost immediate carnage, but there's some individuals in this population that are really pretty well prepared because they've faced crabs in the past. And so rapidly the population evolves up to be even better at dealing with this stress than it was before. But let's take this other population over here. This is a population that has not experienced crabs before. And let's see what happens if all of a sudden we throw in a bunch of green crabs. And this is what happens, by the way, when human beings introduce new organisms to an area. All of a sudden, the local organisms, local plants and animals, are confronted with something unlike anything they've ever seen. Will they evolve? Yes, they will. But the question is whether they can evolve rapidly enough. Frequently what will happen is that even a population that has a certain amount of genetic variation in it will be completely overwhelmed by the new stressor. It wasn't evolutionarily prepared, and even if it changes very rapidly, that rapid change won't be fast enough to save it from extinction. Your book discusses the problem of avian malaria on the Hawaiian Islands. This is another one of these situations where a population is confronted with a challenge that it had never experienced before in many, 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 many generations. And this scenario has played itself out on islands all over the world. Island species are often unprepared evolutionarily for the sort of challenges that come when human beings arrive and accidentally bring goats or rats or crabs or avian malaria. And when those challenges suddenly appear, very frequently, island species can't evolve fast enough to avoid extinction. So let's go ahead and review the key points that I want you to take away from this lecture about the process of evolution by natural selection, how it works and how it doesn't work. Very importantly, organisms do not change genetically during their lifetimes. They don't direct their own evolution, and the environment does not change them genetically so they start showing new traits that they weren't born with. They also don't get to decide what their offspring look like. Organisms do not get to change their offspring so their offspring are better suited to the environment. Finally, needing to have a particular trait doesn't make that trait come along. The process of mutation is completely random. Mutation might generate a trait that is very useful, or it might generate a trait that is really harmful to an organism. In fact, if you have a large enough population, mutation is constantly cranking out new changes of both kinds, useful and harmful. The reason that we start to see only the useful ones as time goes on is because natural selection filters out the ones that are harmful as though they never existed. That's the basic idea that I really want you to have a good grasp on when it comes to evolution by natural selection. The way it works is that natural selection removes organisms that are not good at meeting some challenge in the environment. This filter leaves behind organisms that have the best solutions. And so over time, what you see are only the organisms that have the best solutions. And that's what we're left with today. Organisms that have these traits that are the best solutions to the environmental challenges those organisms face. Please do keep in mind that natural selection does not make the new solutions happen. Natural selection has to wait for mutation to provide a new idea, a new variation, and then natural selection can take that idea and run with it. Mutations are random. They are not intended in any way to solve a problem. Finally, and most importantly for environmental science, neither mutation nor natural selection can look into the future. One of the most dangerous things for a species is to be confronted with a challenge of a kind that it has never experienced before in all of its evolutionary history. And that's exactly the kind of challenge that human activities pose for many organisms worldwide. This is particularly true for island species, which have often been isolated from the types of challenges that mainland species experience for very, very long periods. Okay, it's time for a quick quiz, and then you'll come back to this page and there's another brief video lecture on habitats and niches.